All right, I just started recording and now I'm going to share my screen. Okay, there we go. Here's my reminder to tell me to record. Last time, a week ago, what I did on accident, I started recording and then I forgot to stop recording. So the file was huge and it took a long time for my computer to process the video file after the class was over. So maybe I'll put this sticky at the end. That'll remind me to stop recording after we're done talking about this problem set. All right, so this was problem set number 15. And the first one says we've got an AC generator. It's producing 100 volts AC at 60 hertz, and the rotor is rotating at 1800 RPM. You want to produce the same output, but with the rotor rotating at only 1200 RPM. How could you change the design of the generator to achieve this? Well, we have an equation that relates the RPM of the rotor to the output frequency. It looks like this. I call this the generator RPM equation. In rotor RPM equals 120 times F, the frequency, divided by P, the number of magnetic field poles on the field. So we want to produce the exact same output, which means we want to keep the same frequency. So F is going to be the same, but we can change the design. And by changing the design, that's going to change the number of magnetic field poles. So we could rearrange this equation to solve for P. Just multiply both sides times P, divide both sides by N, and you get this equation, P equals 120F divided by N. It's the same equation, just rearranged a little bit. And now we can solve for, well, how many magnetic field poles did the generator have initially? And then we can solve for how many magnetic field poles do we need to have in our new design. So if we plug the numbers in, I'm taking this equation, plugging numbers in for 60 hertz, that's our desired output frequency. And that is our initial rotor speed. And we find that initially the generator was a 4-pole generator. So the magnetic field would go north, south, north, south. And now I want to produce the same output, but at 1200 RPM. So no problem. I just plug in 1200 in the denominator instead of 1800. And I find that my new generator needs to have a 6-pole magnetic field. And it says to draw a diagram of your design. There's basically 2 ways you can do this. You can put the magnetic field on the rotor, or you can put the magnetic field on the stator. So I drew both of them here. So your sketch should look something like either that or that. If you put the magnetic field on the stator and have the armature on the rotor, then it would look something like this, and it would have slip rings that I didn't draw right here. It'd be like right here and here, you'd have slip rings and brushes. But I just drew the armature and the field. The important thing here is that you've got 6 magnetic field poles, 1, 2, 3, 4, 5, 6, and that they alternate north, south, north, south, north, south. So that would work. Or I could put the magnetic field on the rotor and put the armature on the stator. So here, this is a single phase design. I've just split the armature coil between the 2 halves. And if I wanted to make it a 3-phase design, no problem. I could draw some additional sections of coil, but to make it simple, this is just a single phase AC generator. And once again, I need to have 6 magnetic field poles, 1, 2, 3, 4, 5, 6, and they need to alternate north, south, north, south, north, south. All right. So there's actually one more possibility here that's more difficult to draw, but I could use electromagnets here on, well, actually I could use electromagnets here, or I could use electromagnets here too. As long as those electromagnets produce a pole here that is opposite the pole here, and that's opposite that, and that's opposite that, and so on and so forth. Same thing over here. I could use electromagnets on this rotor as long as those electromagnets produce a magnetic field that alternates north, south, north, south, north, south, and so on and so forth. All right, so these are basically the 2 options for designing your new generator. Number 2 says we have an AC generator. It's producing 100 volts AC at 60 hertz with the rotor rotating at 1800 RPM. So that's pretty much the exact same thing that we had initially in number 1 without changing the physical design of the generator. So now we can't change anything like the number of poles. We can't change the design of the generator, but could I still produce 50 hertz AC electricity? How could I do that? Would there be any other notable side effects to this operational adjustment? So we're changing something about the operation of the generator, not the design of the generator. If we change the number of magnetic field poles, that's changing the design of the generator. But is there anything I could do to take that same generator and produce 50 hertz AC? Well, we have our generator RPM equation again, and we say that, well, the generator RPM equation says that the rotation speed is equal to 120 times the frequency divided by P. So if I'm not changing the design of the generator, P stays constant. Number of magnetic field poles stays constant. But if that stays constant, then I can see there's a direct relationship between the speed of the rotor and the output frequency. So if I wanted to produce a lower frequency, all I'd have to do is reduce the speed of the rotor. So what I need to do here is, if I want to get 50 hertz instead of 60 hertz, I need to rotate it at 50 60ths or 5/6 of the initial rotor RPM. All right. I could also use the equation that I did up here. I can find that it's a 4-pole generator, but that doesn't really matter for this equation. Yeah, it's a 4-pole generator, and we want to produce 50 hertz output frequency. But what we need to do, we can see by this equation, if P is constant, can't change that, then there's just a direct linear relationship between the RPM and the output frequency. So we need to slow the rotation speed to 50 60ths of what the initial RPM was, which is 83.3%. So 1800 RPM, which was the initial RPM, times 5/6 equals 1500 RPM. You could do that in a slightly different way too. If you find that it's a 4-pole generator and you know that your output is 50 hertz, you can actually plug those two things into here, and you'd see that your output RPM, your RPM needs to be 1500 RPM. So there's kind of two different ways of doing this problem. But are there any other side effects to this operational adjustment? Yes, there are. Take a look at Faraday's law. Induced voltage equals negative N number of turns in the coil times the change in magnetic flux divided by change in time. If I slow that RPM down, then for a given angle of rotation of the armature, let's say, rotating from here to here, or I should say rotation of the rotor, whatever's on the rotor, for a given change in rotation, from here to here of the rotor, delta T is going to be larger. It's going to take longer to rotate through a given arc of rotation for the rotor. So if delta T increases, then we are dividing by a larger number, and our output, our result, will be smaller. So this is going to reduce our output voltage by the same factor, because it's all linear in here. There's no exponents or anything. So it's all linear relationships. So if I reduce the frequency by 5/6, then I will also reduce the output voltage by 5/6. So instead of 100 volts AC output, I'm now going to get 83.3 volts output. So this actually is a good illustration of why you can't just take a generator that's designed to produce 60 hertz and ship it across the world and have it operate and produce 50 hertz. It won't work very well. You'll get a different output voltage. So you can't take a generator that's designed to operate in the US or Canada and ship it over to Europe or Asia and have it operate, because it's not going to operate correctly. It has to be designed with the particular voltage and frequency in mind. Number 3, this one's pretty simple. It's a 3-phase AC generator. Here's the phase windings, phase A, phase B, phase C, for example. It's producing electricity at 60 hertz. How fast is the rotor rotating? So in this case, we have the magnetic field on the rotor, You can see the little N and the little S that tells you this is the magnetic field. So we've only got 2 poles, 1, 2. So our frequency is 60 hertz. Our number of magnetic field poles is 2. So just plug that in. N equals 120 times F, which is 60 hertz, divided by P, which is 2. And you get 3,600 RPM. All right, number 4 is a fun little Faraday's law equation. It says we have a coil on the rotor of a DC generator. All right, as it turns out, it doesn't really matter if it's an AC or DC generator. Faraday's law works the same, whether it's an AC or a DC generator. All that changes is the output. So we have more windings on the armature, and we have a split ring commutator instead of slip rings, but Faraday's law works the same way, whether it's a DC or an AC generator. We have 500 turns of wire in a circular shape. That's important to know. It's a circle. The coil is exposed to a magnetic field that changes from 1.0 Tesla, so that's B1, to 0.2 Tesla, so that's B2, in 0.1 seconds, so that's delta T. The output voltage is 100 volts. What is the radius of the circular coil? So clearly we're talking about a relationship between the number of turns, the magnetic field, the output voltage, the time. So clearly this is a Faraday's law problem. So I'd just write down Faraday's law and then start writing down what you know. So you know that N is equal to 500 turns. Delta T is 0.1 seconds. The induced voltage is 100 volts. So now we've got that and that and that. And all that's left is the change in magnetic flux. And we know that is phi2 minus phi1, which is just B2A2 minus B1A1. Or we can factor out the area and say that it's equal to the area of the armature times B2 minus B1. And we know B2 and B1. B2 was 0.2 Tesla and B1 was 1.0 Tesla. So we know that our change in magnetic flux is equal to negative A times 0.8 Tesla, or the way I wrote it, area times negative 0.8 Tesla. Either way, you plug that in to your value for the change of magnetic flux, and you can plug all these other known values in as well. And now the only unknown in this equation is the area of the armature. So you can solve for that. The negative signs are going to cancel out here and here. And you're going to multiply both sides times 0.1 seconds and divide both sides by 500 turns and 0.8 Tesla. And your answer then, remember your area is always going to be in meters squared. So your answer is 0.025 meters squared. Now that's probably the hard part, but it asks for the radius of the circular coil. And we now have the area of the circular coil. Fortunately, it also tells us it's a circle, and we know the area for a circle is pi r squared. So if I know the area of a circle, I can solve for the radius of the circle. So in this case, the area is 0.025 meters squared. Plug that in, and now I'm going to divide by pi on both sides, and then I'm going to take the square root of both sides to get r. So divide both sides by pi, then take the square root of both sides, and you're going to get r. Remember, when you take the square root of meters squared, you're going to get units of meters. So the answer is 0.089 meters, or if you want to convert to centimeters, no problem. Just move the decimal point 2 places to the right, and you get 8.9 centimeters. Okay, number 5. The rest of them are pretty easy. The machine in number 4 is connected to a heating element with a resistance of 6 ohms. What is the power dissipated by the heating element? Well, power is equal to current times voltage. We know the voltage. It actually told us it was 100 volts. But what's the current? We don't know what the current is, but we can solve for it because we can use Ohm's law. V equals IR, or solving for I, the current, I equals V divided by R. Plug in your voltage, plug in your resistance from the problem, and you get 16.7 amps. So now I can plug into the power equation, plug in for I, plug in for V, and you get 1,670 watts or 1.67 kilowatts, either one. And lastly, in number 6, it says the heating element in number 5 is left on for 8 hours. How much energy has it consumed? Well, we have our equation for energy. Energy is power times time. And we know the power from here, and it's on for 8 hours. So we take these, multiply them together, and we get 13,360 watt hours or 13.36 kilowatt hours. All right, so I'm going to stop recording, and then if anyone has any questions,